Hi, welcome to our first online lecture for SCI8511. So this is how it's going to go. I'm going to record these topics. You'll see the slides online. There'll be a blank set and there'll be the filled set, which is what we'll go through here. You can watch this if you need to. I'll be walking my way through it. And then during our normal class time, we'll have Zoom meetings where you can bring anything you want to ask, but you'll be doing the material on your own time when it's convenient. All right. So, my thing's not working. There we go. We have a test coming up. That's what the point of this slideshow is, to review for that test. So this week, you are just going through the topics that are going to happen, and then it's going to be online. It'll be multiple choice online. It'll be like our quizzes, but I'll change the availability. So starting at our usual class start time, be it 12 p.m. or 2 p.m., the test will be available. It'll be available all the way until midnight, and it will have a 3-hour time limit, so you have to complete it in that time. The location of the test will be in the test to review, which is exactly where you found these slides, hopefully. Okay, so here are the topics that you're going to get on this test. A little bit about resistivity, Ohm's Law, all the types of circuits, and then we'll look at understanding what happens when you have an open in a circuit or a short in a circuit. So here are my resistivity questions. Looking at number 1, what is the resistance of a 25-meter long wire? The resistivity of copper is 1.72 times 10 to the negative 6, and the wire, we're given a diameter. So we know that a resistivity formula to find resistance is equal to rho, which is the resistivity, times the length of the wire divided by the cross-sectional area of the wire. I want all your measurements to be in centimeters because our resistivity is given to us in centimeters. So when I do this, I'm going to have my resistance is equal to, I'm not going to change the resistivity. I'm going to leave that at 1.72 times 10 to the negative 6. But I am going to change the meters to centimeters. If I have 25 meters, I need to divide by 100, so I'm going to have 2,500 centimeters. Multiply by 100, not divide, my bad. And we're going to have that over the cross-sectional area. Now, a wire is always a circle in this class, so we're looking for the area of a circle. The formula for area of a circle still is pi r squared. For the radius, we're given a diameter, so let's change that to a radius by dividing by 2. So the radius of this wire is 1 millimeter, but I want the radius in centimeters. So I'm going to divide by 10 to change that 1 millimeter into 0.1 centimeters, and that's 0.1 squared. Okay, so when you do all of that math, you should be able to go through, and you're going to have, hopefully, this answer. Okay? And that's just it. Like, wires are really low resistance. We consider them to be 0, so we don't expect to see a large resistance value. So let's look at number 2. How long is the wire? With an area, and a resistance, and a resistivity. So we are solving for length in this one. But we're going to set up the same way, and just put everything in the right place. The resistance that that wire has is 0.5 ohms. Same resistivity as the last question. It's a pretty common value for copper at 20 degrees. Okay, length is our unknown. And I don't have to do anything because this is an area, so I can just put the 0.25 directly in. It's already in centimeters squared, so that's perfect. Okay, as per usual, there's lots of ways you can go about this, but I find that the algebra is easiest if you just leave the 0.5 alone for now and divide the 1.72 times 10 to the negative 6 by the 0.25 below it, just to clean up the right side of the equation. So when you do that math, it's the same as multiplying by 4, and you're going to get this value. I'll put some brackets around it because it's still multiplied by the length. Okay, and then to isolate L, you divide both sides by 6.88 times 10 to the negative 6, so 0.5 divided by 6.88, sorry, times 10 to the negative 6, and that should give you a very big number, 72674 centimeters, which you can divide by 100 to make 726 meters if you want, but I will accept the answer either way. Next, we're going to just briefly touch on Ohm's Law, and you know that's our triangle that has, come on baby, V or E, whatever you prefer, is equal to current times resistance. So, same. Look at the question. We're given a resistance. It's 35 ohms. We are given a voltage. It's 10.5. Whoops, 10.5 volts. Okay. What's our math? If we look at our triangle, if we want to solve for the current, we're going to take the voltage, the 10.5, and we're going to divide by the resistance. When we do that, we should get 0.3 amps, so a small current. So will it blow a 2 amp fuse? No. It should be fine. Okay, let's look at our second one. This time we have a resistance. We have a current, 300 milliamps, but I'm going to divide it by 1,000 to change it to amps. Keep the base unit when you do this, so 0.3 amps. Okay, and we're solving for a voltage. So looking at our triangle or formula sheets, we know that the voltage is going to be the resistance times the current, which is going to give you 600 volts. Done and done. These questions are pretty straightforward, so I'm expecting you to do well on them. Let's look at series circuits. What do we know about series circuits? We know that the sum of the resistances, RT, is equal to R1 plus R2 plus R3, however many resistors. Here we have 3. So in order to find the total resistance for this circuit, let me just fill in my thing here first. I've got 7, 9 ohms, 21 ohms. Okay. All right, so to find this value, 7 plus 9 plus 21 should give you 37 ohms. And like I said, when you have 2 pieces of information in a column, you have the math to get the third. The total current is equal to the total voltage divided by the total resistance. So we're going to take 54 and divide it by 37, and that should give you about 1.46 amps. You can round to 1.5 and just make your answers a little different. Now, what do you know about current in series? And this is important. You have to remember this. Current in series is the same across all resistors. So we're going to have 1.46 amps everywhere. That's fine. How do I solve for each voltage? 7 times 1.46, 10.22 volts. 9 times 1.46, 13.14 volts. 21 times 1.46, 30.66 volts. Now, ideally, if you add those things together, 30.66 plus 13.14 plus 10.22, you should get your source voltage. In this case, I think they're going to be like 54.02 volts. Close enough. That's because of rounding. All right, parallel circuits. So I'm going to fill in my resistances that are given to me. 7 ohms, 9 ohms, and 12 ohms. So what do we know about parallel circuits? Well, finding the total resistance is a pain in the butt, but that's just life. So when we look at a parallel circuit, we are going to have to find the resistance by using the reciprocals. So the total resistance, the reciprocal of the total resistance, will be equal to 1 over 7 plus 1 over 9 plus 1 over 12, our 3 resistances. Okay, and that's where those numbers are coming from. Now, I talked in class about using the reciprocal button on your calculator. That's super handy. At the end of the day, do what you got to do to get these three fractions added together. You can use decimals, but you should get this when you do those three fraction additions. Now, make sure you know to get the reciprocal, you are going to take that answer and do this math, or press the reciprocal button on your calculator, and you're going to get a total resistance of 13.1 ohms. And that should be good. Oh, no, this is the wrong question. Never mind. Let's erase that. 1 second. We'll try the eraser. See if this works for me. My bad. I was wondering why it was higher than everything else. And let's go back to the pen, hopefully. There we go. Okay, so let's look over here. 2.96 ohms. Better, better, better. It should be smaller than the branches. Okay, 2.96 ohms. All right. Once again, you've got voltage. You've got resistance, which means you have current. I'll just make my decimal a little better. Oh dear. So you have current, which is going to be equal to 4.05 amps. 12 divided by 2.96. Okay, so is current the same in all three branches? No. Current splits when you go into parallel. It doesn't split evenly unless all the resistance are the same value. It likes the path of least resistance. So I expect to see the most current across R1 and the least current across R3. But what I do know about parallel circuits is the voltage is constant across all the loads. So here, because I don't have anything other than this one parallel branch, I know that I'm going to drop 12 volts here, I'm going to drop 12 volts here, and I'm going to drop 12 volts here. And then I just have to do the math. 12 divided by 7, 1.71 amps. 12 divided by 9, 1.33 amps. And 12 divided by 12, 1 amp. And once again, when you add 1 to 1.33 to 1.71, you should get pretty close to your total circuit current. Okay? All right, so let's ramp it up. Combined circuits. So combined circuits are all about redrawing. I've got a 10 ohm here, I've got a 32 ohm here, and I've got a 19 ohm here. Okay, so when I look at this circuit, I kind of start and I go through, and I just have one parallel branch. This one's pretty easy, right? So I have one parallel branch, but I have two resistors in the top part. So they're in series with each other, so I can add them. And I can really, what I'm doing is I'm creating an equivalent circuit, which, pardon my drawing, is going to look like this, where this is the total of R1 plus R2. 10 plus 32 is 42 ohms. This remains 19 ohms. So now I'm just solving a parallel one. And the bonus is I'm solving a parallel circuit which has only two branches, so I can use that cheat where I can find the total resistance of the parallel thing is equal to the product of the two resistances divided by the sum of the two resistances. There we go. And you're going to make sure that you do that addition. So you're going to take whatever is and divide it by 61. All right. When you do that math, this time, I should get my 13.1 ohms. Perfect. Okay. Here we go again. 115 divided by 13.1, 8.8 amps. So I know that it's not going to be 8.8 amps in both branches. I know that it's not going to be 4.4 amps in both branches because they're not equivalent, like 42 and 19 aren't the same resistance. So I just need to look back at my original picture, and I'm looking for something because the only place I'm dropping the voltage is across this parallel bank. So I'm looking for a single resistor where I can drop all 115 volts, and that's at R3 here. So I know that R3, all the voltage drops. And then once I do that, 115 divided by 19 gives me 6.1 amps. Okay, so I know 6.1 amps went down here. How many amps went up here? Well, that's just subtraction. 8.8 total current. Subtract 6.1 that went into the R3 branch, and that should leave you with 2.7 amps. Now, R1 and R2 are in series, so I know that each one of them gets 2.7 amps. And then the math, just multiply. 2.7 times 10 gives me 27 volts here, and 2.7 times 33, I can't even read my own writing, but I think it's 86.4 or 88.4, something like that. And once again, you're looking for that to total approximately 115 volts. So let's keep going with these and do a few more examples. Okay, got a lot going on in this one. But the first thing you're always going to do is make it look like something more friendly. And we're going to do this in a couple steps. First, we're going to kind of do the same thing we did in the last one. And there's my R5 just floating. Whoops, floating over there. There we go. Boop, boop. I've got an open in my circuit apparently. Okay, put in my values. R1 is 5, R2 is 10, R3 is 4, R4 is 20, and R5 is 8, and 115 is a voltage. Okay, so my first simplification is to combine R2 and R3. They're in series with each other, so I can just add them. This is equivalent to 14 ohms. My next simplification is going to be to make 3 resistors in series. And all I'm doing is taking this 14 and 20 piece and changing it into something here. Okay, so I'm going to use the cheater. R equals 14 times 20 divided by 14 plus 20. Okay, whoops, this is very ugly. So we're going to get, hold on, I've got to get another piece of paper here. I'm looking at the wrong page again. Okay, R is equal to 14 times 20 times 14 plus 20, and you should get about 8.2. Oops. Okay, so now my new circuit, I go through that R1 in series. I've made an equivalent resistance for all this hot mess, which is 8.2, and then I go through my R5, which is 8. And at this point, I can add them. 8 plus 8.2 plus 5, total resistance, 21.2. Step 2, same as always. 115 divided by 21.2, 5.4 for the circuit current. Okay, now I look at my picture. Who gets 5.4? Anyone who's in the outermost circuit in series gets 5.4. So I look and I see R1 is a plain old series resistance. It gets that. And I see that R5 is plain old, so it also gets that. Then I do some math. 5 times 5.4 gives me 27 volts here. 8 times 5.4 gives me 43.2 volts. Okay, so now I want to know about the voltage drop in the parallel branches. So I know that I had 115 volts and I dropped 27 and I dropped 43.2 and I have a leftover that is 44.8 volts. Okay, so when I look at this picture, I'm going to send 44.8 across here, and I'm going to send 44.8 across the 20 ohm. The problem is this 14 is equivalent. It's a 10 and a 4. So some of it's going to drop at the 10, some of it's going to drop at the 4. So I'm going to ignore that branch for now, but there's only one resistor in the bottom. So I know that R4 is going to drop all 44.8. Okay. And if I want to find the current across R4, 44.8 divided by 20 gives me 2.2-ish. Excellent. So now I know that I had 5.4 amps coming up to that parallel branch, and that 2.2 amps went to the bottom part. So to find the part that went to the R2 and R3, 5.4 minus 2.2 equals 3.2 amps. R2 and R3 in our original drawing are in series, so they're each going to see that 3.2. And then you're going to do the math to solve the rest of the circuit. 10 times 3.2 is 32 volts. And 4 times 3.2 is 12.8 volts. Okay. And like I said, my questions could be anything. They could be like, what's the current across R3 or the voltage drop at R5? But when you do this table, you know everything. So you're ready for any question I'm going to throw at you. Let's do one more example. Ramping it up even more. I don't think we've done one like this. So we have a lot going on in this picture. First, I'm going to fill out my table. R1 is 5. R2 is 20, R3 is 5, R4 is 6, and R5 is 10. So, pure series components, I only have R5. I've got like a double down parallel thing going here, but that's fine, because I can flatten this into an equivalence resistance, change R2 and R3 into one thing, and then I can add that to the 4, and then I can flatten again, and then I will have a relatively simple circuit. So let's draw what we're going to do. So we're going to come in, there's our R1, and we're going to change R2, R3 into something, and we're going to leave R4 alone, because it's still in a series parallel there. And then we have R5 just floating around out here. For this one, oops, not that one. For this one, the R2, 3 is going to be 20 times 5 divided by 20 plus 5, which is going to be 100 divided by 4. Sorry, 100 divided by 25, which equals 4. So we get, this is 4 amps right here. So now I have 4 here, I have 6 here, I still have 5 here. It's not super exciting to me right now, and I have 10 down here. So, next step, you got 2 in series, simplify it. So simplify, simplify. Leave the 5. This is going to be added together, and you have your little 10 floating down here still. Okay, 5, 10, 10. Here, same trick. The resistance of that is equal to 5 times 10 divided by 5 plus 10. So your resistance is going to be 3.3 ohms. Excellent. And now we essentially have a circuit that looks like this, where you have 3.3, whoops, and you have 10, and this is series, so you add them together. I know you did all the work up here, but don't forget about the 10. 3 plus 3 plus 10, 13.3. Okay, 80 divided by 13.3, 6 amps. Right back to the original picture. Who gets 6 amps? The only place that current hasn't split is right here, because it split a whole bunch in here and it came back to 6 amps. But R5 gets that full 6. So we're going to write 6 here. And that means that we're going to drop 6 times 10, 60 volts across R5. Wow, we used up a lot of it. So what do we have left over? $20 volts for the rest of it. Okay. Which one of these things is actually going to get 20 volts? Well, if I look here, there's a whole bunch going on, like another parallel thing and another resistor. They're all going to get some amount, but the top branch only has one resistor. So I know that if I look at R1, it's going to get the full 20. 20 divided by 5, which means 4 amps went up there. So I used 4 amps this way. What goes this way? 2 amps. Why? Because 6 minus 4 is 2. Okay. Now, it's going to split again in the 2, 3, so I'm going to ignore that one for the moment, and I'm going to look over at the 4, because it'll come back together and be 2 amps across the 4. So I can go over here, put my 2 amps in, 6 times 2, 12 volts. Okay. So that means I had 20 volts in that entire branch. I had 20 volts coming in here. right? The 20 volts we had there. I am going to use 12 of it here. So the leftover for this little R2 3 parallel bank is 20 minus 12, 8 volts. And R2 will get 8 volts, and R3 will get 8 volts. And then 8 divided by 20, 0.4 amps, and 8 divided by 5, 1.6 amps, and guess what? 0.4 plus 1.6 equals 2. So that's perfect. All right. Let's talk the last topic for this little lecture. What happens when you have opens in series? What does an open in series look like? It looks like you broke a wire. So let's say we should have had 2 resistors and instead we just have, what happened here? 1. There's no connection, so there is no current flowing. And the resistance, we call it infinite, right? Because it's just not going to happen. So it's infinitely resistant. So that's my infinity symbol. What about in parallel? Pure parallel? So the resistor that was there is gone, right? So what has it turned it into? It's turned it into a series circuit. Now the series circuit is always going to have more resistance than the parallel circuit. So your resistance is going to go up. And if we know that V is equal to IR, and the R goes up, but the V isn't changing, I have the same supply voltage, the current must go down. Okay, there we go. Now, let's say we have a combined circuit. There we go. La, 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 la. So we kind of have to have 2 situations here, the series and the parallel. If I open across the series part of the circuit, what happens? It's the same as the other thing. We have no current flowing. I don't know why I keep doing that. I have no current flowing. Make a 0. There we go. No current flowing. And then the resistance is infinite because there's no current flow. Now, if I open it up in parallel, you're just going to get rid of, say, this branch, and it becomes a series circuit. And like we said, when you have this series component, your resistance is up, and you're going to see a drop in current. Shorts. So if you have something in series, and you create a short. A short is like when you take a resistor and you make it a wire. So it really kind of turns this little circuit into a 1 resistor circuit. Resistance is down. Therefore, current is up. If you are in parallel, and this is a pretty nasty situation if this happens and you don't have circuit protection, because when I take this and make it into a wire, I'm essentially creating this situation, because no current is going to go down the path with the resistance still in it when it can go down a straight wire. So resistance is 0, essentially 0, so your current goes way, way, way up, and you're going to blow your fuse or melt something. And if you have a combined circuit, when you take series part and the parallel part, when you get rid of the resistance of the series thing and make it a wire, you just turn it into a plain old parallel circuit. So yeah, you're dropping some resistance, right? So you're increasing the current. Likewise, if you make this a wire, you're going to drop the resistance and increase the current. So just be aware of how to walk around those kind of situations. So that's it for all now. Hopefully this works. I have no idea. I have no interest in rewatching it, so I'm hoping it's good.